Hello, my name is Mateo Torrejon, and welcome to Lab 1 Constant Velocity, Section A. Introduction. So, the purpose of this lab is to observe and calculate the motion of a specific object that is moving at a constant speed, as long as it does not change the direction. What this means for this lab is that as long as there is no change in the sign or the magnitude of velocity. We do this by pushing an expo marker across the table, recording the movement of the object, and then through a computational model, we have measured the change in the position over time through tracker, which also allowed us to graph a position over time curve with glow script. Our assumptions before were that there were no friction, no air resistance, no more force is the gravitational force, our surface is flat, and there's only change within the x-axis and not the y or z-axis. Our assumptions after were that our observed model predicted with the final position of our system, which was the object, was under the experimental model, which likely meant that there were other external forces that were acting on the system. So for our main physics ideas, we started with Newton's law. So Newton's law, first law, which is the law of inertia, which is an object at rest stays at rest, and an object in motion stays in motion at a constant velocity unless acted upon by an external force. This means that if an object, which was our rolling expo marker, is already moving, it will continue moving at the same velocity unless a force like friction slows it down. The marker should move at constant velocity if there is no net force acting on it. And we also use Newton's second law, which is the law of acceleration. The acceleration of an object depends on the net force acting on it and its mass described by the equation F is equal to ma. And we also use the position update formula, which was used in our tracker and our glow script code, and as well as the velocity update formula to understand that our velocity that we wanted was constant. So first, the specific models that we used was Tracker, which is a computational model in which we put in our video of the expo marker rolling across the table, and it gave us a position versus time graph. And then with the glow script code, we used the iterative process of updating position in order to update those positions at each point that was indicated by the tracker. However, the tracker was used for our experimental graph, and then the glow script was used for our actual graph. We had to also set up the experiment. So the first thing that we did in order to measure constant velocity was that we wanted to record a video of an expo marker rolling through a table. So we pushed the marker and then we let it roll through the table and recorded a video on top of it at around 90 degrees of an angle. And then second, we exported that video into Tracker and used the software to put the expo marker into the axes through Tracker and get 98 points of position over time to then allow us to get our experimental graph. Then we went to GlowScript and ran a program that mathematically updated position over time in order to create a set of data that we compared to the tracker data and see if our velocity was indeed constant. And then finally, we then inputted our data into an Excel sheet to create the graph to compare our data to allow us to make our final assumptions. So after recording the video, we imported it into Tracker, which we identified the system as the blue X marker, so we put its dimensions, then the surroundings, which were the table and the air, with the initial conditions with a position vector, with a velocity vector, with the time starting at 0, with a delta t of 0.033 because our FPS was 33, with an Fnet of around 0, and our mass of 0.01 kilograms. And then, using our initial conditions, we changed our glow script code in order to create a position versus time graph that showed a linear relationship which indicated that there was indeed a constant velocity for our expo marker. And then using these two different position versus time curves, we could compare them, which we will later put into an Excel sheet, which we will show after. So then finally, we put our tracker data and then we put our glow script data into an Excel sheet, which allowed us to create a graph showing both of the position versus time curves in a single graph, with the time being on the y-axis and the position being in the x-axis. And so we can see that our orange, which is our glow script code, which is a constant velocity, versus our blue, which is the tracker, which shows that there is not a constant velocity because it's under the constant velocity curve, which indicated that there were other external forces acting on the system, which is our expo marker. So we could see that there were possible errors with our experiment. So possible errors include systematic errors because of course you cannot constant velocity because there is friction between the table and the expo marker, and there is also air resistance to account for, and there could have been human error with tracker inconsistencies. Perhaps we put the center of mass in the wrong direction, or we perhaps did the axes wrong, or there could have been variations in the force that we applied. finally, what does it mean? It is not entirely possible to calculate all the forces that are acting on the exponent marker, and so the reason for this is that we will need to know the exact force acting on the exponent marker from the push at the start, the force of the friction, and the force of the air resistance, of which we do not know of. Thank you so much.